Hello, in this module, we are going to talk about using op-amp as a comparator. So we will address this question whether or not we can use operational amplifier, popularly known as op-amp, as a comparator. And we will also see what is the difference when we use op-amp as a comparator or we will use comparator as a separate and dedicated circuit. So in the market, there are two types of ICs available. One is operational amplifier and one is a dedicated comparator IC. So out of these two, which we will figure out which one to use and when, and the fundamental differences between them. And we will also cover a few important points linked to the comparator. So before moving forward, let's have a look at operational amplifier. So as we know, as the symbol says, the operational amplifier is basically a difference amplifier which has two inputs named as positive and negative, and it is labeled as V1 and V2. And this op-amp amplifies the difference between the two inputs called as VID. So VID is basically V1 minus V2, and we take a magnitude of it so that you have output in the which is a gain times VID. So that is your output. And op-amp is designed to work with a negative feedback. So whenever you want to use operational amplifier for linear applications such as amplifier, filters, instrumentation amplifiers, etc., we use a negative feedback, and based on that, we can have inverting type of amplifier or non-inverting type of amplifier. And using a negative feedback means we feed some portion of the output back to the input through some resistive element. For example, I'm feeding the output of this amplifier back to the negative input of this amplifier, and accordingly I will create the negative feedback. So the output stage of this operational amplifier is designed in a such a way so that we can use the negative feedback, and based on that we will always operate the operational amplifier in its linear mode of operation. Now what is the linear mode of operation? So for that we can take a look at the input output characteristics of the amplifier. Let's say this is your VID and this is your VO. So this is your VO actually, and this is your VID. So what you see here, we can draw such line. So not right this way. We should draw it right from the center actually. So it would be like positive and the negative excess. And in the center, you will see that this is the operation, and here are your supply rails, for example, not that far. Yeah, so you can see this is an output and this is your input, that is VID and the VO. And transfer characteristics of the operational amplifier can be drawn like this. So for the positive VID, you have the positive output, okay, and for the negative VID, you have a negative output. And this region is called as linear region of the operation, okay, where you can have the positive and the negative voltage difference that results in your proportional output, okay. On the other hand, comparators are designed to work in the saturation region. Saturation means you have a supply rails right here. Let's say this is plus VDD and this is minus VEE, or just say VEE. So these are the supply rails and your output is bound to saturate, is bound to saturate after a certain threshold in the output. So if your differential voltage exceeds a certain threshold, your output is switching to the positive rail or switching to the negative rail. And that's how precisely the comparator can be used as a circuit, as a switching circuit. So let's have a look at the comparator. There are positive types of comparator, like in an inverting way and in a non-inverting way. So the circuit right now here shows us your input is of this triangular waveform, half triangular waveform, that is connected to the positive input, and the negative input is tied to a voltage reference created through this two resistor combination, which is a potential divider or a resistor divider. So you have a VCC, which is your positive supply rail, you have a ground, which is your negative supply rail, and output with respect to ground can be taken. So here is the input output waveform, input output waveform of the comparator, and that helps us to explain the behavior of the comparator. So the reference voltage, as indicated by the red line, is set to V reference, which is half of the VCC, and this is how we see that. And your input is in green, it starts from 0 and it goes on increasing. As long as it is below the reference voltage, your output is set to 0. Output is as shown in 0 for the condition V in is less than V reference. However, as soon as your V input increases and it goes beyond the threshold of V reference, your output switches to the positive supply rail, which is the saturated output voltage, which is also shown right here in the transfer curve. Now, your input starts decreasing, but it is still above the reference voltage, so output is at a positive saturation level. As soon as the input falls below the reference, your output falls to 0. Okay, so you can see that your input is 0 for the for its value below the reference. Your output is 0 for the input values less than V reference, and your output is 1 for the input values greater than the V reference. So that is how the comparator are used. Okay, so output stage of the comparator is specifically designed to work in the saturation region, meaning that the output voltage is always close to one supply rail or the other, but not in between. Okay, unlike your operational amplifier used as some other applications such as filter or amplifiers, etc. Okay, so in general, if the given design calls for a comparator, it's best to simply use a comparator, because such device is designed and optimized specifically for that function, and hence it will provide you the best results. But there may be a situation in which using an op-amp for the comparator is attractive choice. For example, if your design contains an unused operational amplifier and you need a comparator, then using an op-amp as a comparator is a better choice. That will save your time, board, and the cost of the overall system. Okay, so comparators are designed to work in a saturation. Second advantage of the comparator is a slew rate. We'll see that in a moment. And as I said, using op-amp as a comparator can save on your time, cost, and the board space. So for example, you have operational amplifier IC in which you basically have the quad op-amp. For example, you have 4 operational amplifier there, and you have used 3 as op-amp for specific application, and there is a fourth one unused, and you need a comparator in your application. So why not use this op-amp as a comparator? Okay, now, slew rate is a very important concern because when your output is switching the levels between positive rail and the negative rail, so slew rate determines how fast it can do that. So you have, as a designer, you have to make sure that whether you use op-amp as a comparator, that should have a high slew rate, or if a dedicated comparator IC gives you a high slew rate, then you should choose that IC instead of using op-amp as a comparator, but depends on your application and your choice of design. The final point I want to highlight here is a comparator with the hysteresis. For example, in this waveform, as I explained, you have a threshold set that is your V reference, and it has only one hysteresis. Okay, and we are using operational amplifier as a what to say, we are using operational amplifier as a comparator. But in a dedicated comparator ICs, you can have hysteresis and thresholds levels dedicatedly designed, and your input should be following those threshold levels. For example, a comparator with hysteresis will utilize an upper and lower threshold in which the input signal must pass above or below these respective thresholds before the output will transition. So in this waveform, you see only there is a one threshold, but in a comparator with a hysteresis, you can actually have 2 levels of threshold. One it's called upper threshold, and right here, one it's called lower level threshold. So the output that is shown here previously is referring to the threshold set by the V reference, but a comparator dedicated IC with the threshold levels upper and lower, your input must pass these levels actually to so that the output can make a transition. Okay, so this is useful for input signal that are electrically noisy or slowly moving. So if you don't have a high frequency signal, then you need to use a dedicated comparator IC. If your input signal is noisy, then you need to use a dedicated comparator IC. In other cases, you can use op-amp as a comparator. Okay, so most comparator ICs offer built-in hysteresis, with some even offering adjustable threshold levels. So these threshold levels can be adjusted. So configuring op-amp as a comparator in an open loop will result in no hysteresis. So you see, we are basically converting the op-amp as a comparator with no feedback, because comparator is a circuit with no feedback. So you don't have any hysteresis. You just set a reference with the help of potential divider, and your input is crossing that, and accordingly the output is switching. Okay, so there is no hysteresis in this case. But if you use a positive feedback, one can add hysteresis to the op-amp configured as an op-amp, configured as a comparator. So let's say you have an operational amplifier and you have a positive feedback. So you have output here, and let's say you have we use this kind of configuration where your output is fed back to the positive input terminal of the op-amp. So in that case, you can have a hysteresis for the op-amp configured as a comparator. So hope you found this information useful. If you did so, share with others like and comment to the videos, and do subscribe to the channel. Till then, stay tuned.